Welcome to this lecture on probability and probability distributions. Today, we are going to explore a fascinating and highly useful mathematical model known as the Laplace distribution. If you have ever wondered how statisticians model extreme, unpredictable events that standard bell curves fail to capture, you are in the right place. Let us dive in and see why this distribution is so important. To understand why we need this model, imagine you're throwing darts at a board. Most land near the center, but occasionally a sudden gust of wind blows a dart far off target. A standard normal distribution might underestimate how often these extreme wind gusts happen. The Laplace distribution is designed exactly for this situation. It is used when most values cluster tightly around a central peak, but extreme outliers happen much more frequently than a standard bell curve would predict. Because it handles these heavy tails so well, it is a crucial tool in our statistical toolkit. Now that we understand the physical intuition, let us look at the building blocks of this distribution. The Laplace distribution is completely determined by just two numbers. The first is the location parameter, denoted by the Greek letter mu. This tells us exactly where the sharp peak is centered, acting as the mean, median, and mode all at once. The second is the scale parameter, denoted by b, which must be a positive number. This controls how spread out the distribution is. A larger b makes the curve flatter, while a smaller b makes the peak even sharper. This brings us to the mathematical equation that defines this shape, known as the probability density function. The formula might look a bit complex at first glance, but it is actually quite elegant. The exponential function causes the probability to drop off rapidly as we move away from the center. However, the absolute value around x minus mu is what creates the signature sharp, non-differentiable peak exactly at the center. If you increase the scale parameter b, the denominator grows and the curve spreads out wider. If you decrease it, the distribution pinches tightly around mu. Before we move on, let us see this with a concrete visual comparison. Here, you are looking at a graph comparing the Laplace distribution in blue with the standard normal distribution in dashed red. Notice the distinct sharp point exactly at the center of the Laplace curve, completely unlike the smooth, rounded top of the bell curve. Furthermore, look at the tails on the far left and right. The blue line sits higher than the red line in these regions. This visually proves that extreme values are much more likely to occur in reality when following a Laplace model. Now that we have our formulas, let us apply them to a real-world manufacturing problem. Suppose a manufacturing error follows a Laplace distribution with a central location parameter of 0 millimeters and a scale parameter of 2 millimeters. We want to find the probability that the error is exactly between 0 and 4 millimeters. To find this, we must integrate the probability density function from our lower limit of 0 to our upper limit of 4. Since we are looking at the region greater than 0, the absolute value simply becomes x. We substitute our parameters to set up the integral. Continuing with our calculation, we simplify the constant fraction outside the integral to make the calculus easier to handle. Next, we find the antiderivative of the exponential function, which gives us negative 2 times e to the power of negative x over 2. We apply the fundamental theorem of calculus to evaluate this from the lower bound of 0 to the upper bound of 4. We carefully substitute the upper limit of 4 and the lower limit of 0 into the antiderivative, subtracting the lower limit evaluation from the upper limit evaluation. Let us wrap up this calculation. We know that any non-zero number to the power of 0 is exactly 1, which simplifies our second term. Distributing the negative sign flips the terms inside the parentheses, giving us 1/2 times the quantity 1 minus e to the power of negative 2. Evaluating this exponential term gives us a final decimal probability of approximately 0.432. This means there is roughly a 43.2% chance that the manufacturing error will fall between 0 and 4 millimeters, helping engineers estimate the daily scrap rate. Having seen how to calculate probabilities, you might wonder where this distribution naturally comes from. One of the most elegant ways to understand the Laplace distribution is by building it from simpler parts. Imagine two identical, independent processes that both follow an exponential distribution, which models waiting times. If we take the difference between these two independent variables, the resulting value perfectly follows a Laplace distribution centered at 0. The positive side comes from the first variable being larger and the negative side from the second. This is exactly why it is often called the double exponential distribution. Let us look at another common scenario that uses this exact concept of competing exponential forces. Imagine two identical computer servers processing requests. The time for each follows an exponential distribution with an average of 3 milliseconds. We want the probability that the difference in their completion times is greater than 6 milliseconds. Because they are independent, their difference follows a Laplace distribution centered at 0 with a scale parameter equal to the average, which is 3. We need to find the probability that the absolute difference is greater than 6. To solve this efficiently, we use the perfect symmetry of the Laplace distribution. The total probability of the difference being greater than 6 in either direction is twice the probability of it being strictly greater than positive 6. We set up the integral for the right tail starting from 6 and going to infinity using our scale parameter of 3. We find the antiderivative just as before. As our variable approaches infinity, the exponential term decays to 0, which is a standard property of improper integrals involving exponential decay. Now for the final steps of our server problem. The upper limit of infinity causes the first term to vanish completely to 0. Substituting the lower limit of 6 leaves us with e to the power of -2. We then multiply our result by 2 to account for both the positive and negative tails, which perfectly cancels out the fraction in front. This gives us a beautifully simple exact probability of approximately 0.135. So there is a 13.5% chance the servers will finish more than 6 milliseconds apart. This heavy-tailed behavior we just saw in our examples can actually be measured mathematically using a concept called kurtosis. Kurtosis tells us if we should expect a lot of wild, unpredictable data points far away from the average. The standard normal distribution is used as our baseline and has an excess kurtosis of exactly 0. In stark contrast, the Laplace distribution has an excess kurtosis of exactly 3. This quantitative difference mathematically proves that it will produce extreme outliers much more frequently. Whenever a real-world dataset shows a sharp central peak and too many extreme values, this excess kurtosis makes Laplace the perfect fit. To easily extract properties like the mean and variance from this shape, we use a mathematical DNA sequence called the moment-generating function. For the Laplace distribution, integrating the probability density function gives us this neat, closed-form fraction. The numerator shifts the distribution to be centered at mu, while the denominator captures the spread influenced by b. This formula is valid only when the absolute value of t is strictly less than 1 over b. By taking derivatives of this function, we can quickly find that the mean is exactly mu and the variance is 2 times b squared. Having explored the math, it is clear this is not just a theoretical curiosity. The Laplace distribution is a highly practical tool used across many modern industries. In finance, it models stock market returns, safely accounting for sudden, massive crashes that a bell curve would miss. In artificial intelligence, a technique called differential privacy adds artificially generated Laplace noise to databases, protecting individual identities while preserving group trends. It is also heavily used in speech recognition and image compression algorithms, where differences between adjacent pixels naturally follow this heavy-tailed shape. We have covered a lot of ground today, so let us summarize the key takeaways. The Laplace distribution is a continuous probability model characterized by its sharp central peak and heavy tails, defined by a location and a scale parameter. It naturally arises from the difference of two exponential variables and possesses an excess kurtosis of 3, making it the ideal choice for modeling data with frequent extreme outliers. Mastering this distribution provides a crucial foundation for advanced topics in risk analysis, signal processing, and modern data privacy. Great job following along.